All right, everybody, section 2.3, exponential functions. So we have two types of graphs when we're talking about exponential functions. One is going to go up to the right. One is going to go down towards the x-axis there. It's going to approach 0. This is known as exponential growth and exponential decay, which we're going to cover more in a second here. But just a few applications of exponential functions before we get into that. So if you remember in Algebra 2 when you learned about compound interest is going to be an exponential growth function. And that's where your money is making you more and more money over time, right? So it might be an investment, might be a CD, something like that. But it's as time goes on, your money is going to keep growing because that money is making you more money, all right? And so the rate of growth is going to increase over time. Debt also is going to follow this if it's unpaid, right? Your debt's going to grow if you're not making the full payment on it or any payment at all. And it has a lot of applications outside of or in other disciplines as well. Like, for example, half-life is going to follow typically some sort of exponential decay. And some other science topics. I know they're out there. I'm not really a science guy. But I do know that these types of functions are very come up a lot in different science courses. All right, so that's the real world application. Now let's talk about what we're doing for this class. So exponential functions are going to follow this formula right here, y equals a times b to the x. There might be other transformations. You might be adding or subtracting in the exponent or on the outside, or there might be negatives. But that's the basic function before transformations. So for a graph to look like this, for it to be exponential growth, that first value just has to be positive, bigger than 0. And the value, the base of the exponent, has to be bigger than 1. All right, so as long as that number right there is bigger than 1 and that number is positive, it's going to be exponential growth. Now, this function, as we go from left to right, this function is always increasing. And this graph, even though it doesn't curve back up, this graph is concave up. Right, it's opening up here. So our graph is concave up. Now, the two ends of the graph. So remember, think about the x-axis. As x approaches negative infinity, so that's talking about on the x-axis as we're moving to the left, what does the function do? Well, the function is getting closer to a y-coordinate of 0. If you were to find all these y-coordinates, they're getting smaller and smaller, but they're getting closer to 0. So as we move left, the graph is approaching 0. As we move right, well, this graph is headed right and up, so that we already have the right portion, so right, and then the y values are moving up. Now, exponential decay. It's also true for this that a is positive. So for both growth and decay, a has to be positive. If a is negative, we actually don't consider either of these. It's just reflections of these graphs. So if a was negative and b is greater than 1, this graph is just reflected down. And then, again, what makes it decay? So a has to be positive, b has to be in between 0 and 1, like a decimal or a fraction that's less than 1. All right, and then if, again, this is considered decay right here. If a was negative, it's neither growth nor decay. It would just reflect it down if b was in between 0 and 1. So this graph, from left to right, this graph is moving down. So this graph is always decreasing. But it still is, even though it doesn't curve back up, this graph is still opening up. All right, so it's still concave up. So both of these are considered concave up here. Now, as we move left forever, so this graph, as we move left, it's headed up towards positive infinity. And as we move to the right, the y value is getting closer and closer to 0, the x-axis. And so it's going to equal 0 right there. All right, we could actually even think about it as having a horizontal asymptote at 0 on this graph. And same thing right here. The graph is getting closer to 0 as we move to the right. All right, so a couple questions here, and then there's one we're going to graph at the end. But find the end behavior of this function. And so really all we have to do is figure out, is it this graph or is it this one? So the first value, the 1/8, all right, that is not going to affect the general shape of the graph, just its sign. So if a is greater than 0, right, which we have here, a is greater than 0, it's positive, and b is bigger than 1, that tells us the graph looks like this. It's exponential growth. All right, and so the end behavior, I'm going to leave that there actually. the end behavior, so as we head left forever, left forever, well, we said before that as we move left forever, the graph is going to approach 0. All right, so as we head left forever, the graph is approaching 0. And as we head right forever, the graph is headed up, so it's approaching positive infinity. That's the first one. Now the second one, so A is still positive, but now that B value is in between 0 and 1. All right, so if this value right here is in between 0 and 1, it's exponential decay. Now the graph looks like this. So as we're headed left, I'm just going to reuse this instead of writing the whole thing again. But now this is applying to number 2. Let's see. So as we move left, the graph is headed up towards positive infinity. And as it's headed to the right, remember that it's approaching the x-axis, which we're going to say is a y value of 0. All right, so that's it for those two. And then one more, we're going to sketch a graph of this function. So this is essentially the graph of y equals 2 to the x, but with several transformations on this graph. All right, and so let's think about what 2 to the x would look like first. So b is bigger than 1, it's going to be exponential growth. So without any transformations, it looks like this. We're not going to worry about plotting a bunch of points. It just has that general shape. To the left, it approaches the x-axis. To the right, it's going up. Now, what does the 1/8 do? Well, we learned in our last unit that this is a vertical dilation by a factor of 1/8. So we'd have to multiply all the y values by 1/8, which is going to kind of squish it a little bit that way. But it's not going to change the general shape of this graph. And so we are essentially going to ignore A on this one. All right, it's positive. That's all we really care about. So while it does change the y values, it's not changing the general shape. Okay, but now we have a -3. It's with x. So anytime it's with x, remember it's the opposite. So that moves it right 3. And then that +1 is going to move the graph up 1. And so if I just took this graph and here, I have 3 there and 1. So let's see. I'm going to move this point right 3 spaces and up 1 space. And it looks like this if I do that. Now, because I moved it up 1, it's not going to approach the x-axis anymore, right? It's going to approach, if I move it up just a hair more, it's going to approach y equals 1. All right, so I want to kind of clearly define that here. And again, this would be, if you're graphing it, it's multiple choice, but you want to pick the one where to the left, it's not approaching 0, but it's approaching 1 now because it was moved up 1. All right, so that's it. We're not doing anything crazy with the graphs. It's just understanding how would those two transformations affect the graph. And then if it was a negative, we would have had to reflect it down first before we moved to right 3 and up 1. All right, that's it for this one, guys. Stay flawless.